So what we're going to do is we're going to transpose this into our formula here. So we have y equals the integral from a to x of e to the t tan t dt. So what we want to do though is we want to talk about, all right, where does that 8 come into play and where does that 0 come into play? Well, if the function is plus c, that c value is your y value. And if it's a, that a is kind of like your x. So what we're saying is, all right, here's my x, that represents a. So this is really like 8 to x of e to the t tan t dt. And then what you're doing is you're essentially trying to figure out, okay, what would that value do or what would happen if I had solved this initially? So your y value is 0. A to 8. So again, you're plugging in here, 0 and 8, and solving for tan t. So when they give you this initial condition and these initial values, what we want to do is we want to essentially plug them into our formula. Plug in 0 for y, plug in 8 for x, and go backwards and solve for a. What's nice is that oftentimes when we do these and we solve for a, we're going to get a to be the same as our x. The only time it really changes is if you have some goofy, crazy functions where y isn't 0. So go ahead and take a minute and solve that for x, or solve it for a, essentially. So take your antiderivative and let's prove that you can get to this. So what could you do if you don't know the antiderivative of that function? Do we know how to take the antiderivative of a product for yet? No, not really. So putting it in our calculators isn't going to help us, right? Because what's your calculator going to get you? The bound of a. So what are your thoughts? How could I figure out this gets me to that? What could we do? If you don't know how to take your antiderivative yet, how could you justify this? The problem is you don't know how to take like the bounds of this. That's what we're talking about. Like,
you set up like one where it's like x to the a is equal to like x to a minus 8 to a, or somehow combine them.
yeah, I mean, for this, what the idea would be is think about what you know about tangent. Think about what you know about it needing to equal 0 and e needing to equal 0. How are you going to get that to occur? Exactly, whenever a equals 8. The only way to get a derivative equal to 0 is to have what? The bounds be the same. That's what I was trying to get to. Like, everybody's like, it was simple. How do you get 0 for an answer? The bounds need to be the same. So that's how we can justify that that a value is 8. Remember, that rule is your favorite rule. Same bounds. Equals 0. So, a equals 8. Thus giving you this. That's why the y value equals 0 is so important. Because you need to know, okay, if it has to equal 0, my bounds have to be the same. Good. How about this one? We have, can you recognize a shortcut when finding the derivative of the integral f of x from 0 to t of d dx of 0 to t 3x squared dx. So what's funny is they changed the bounds up on you, right? So before you used to always have f of t dt, and we had 0 to x. So does it change the process? Is this still a fundamental theorem of calculus? Yeah. So the problem, or the process, or the shortcut is still the same. It's plug in the upper bound, know the lower bound is going to zero out, and multiply by your derivative. So don't let like a change of variable essentially throw you off either. And again, the directions are not necessarily always going to say use the fundamental theorem of calculus. So this right here is just you being able to recognize taking the derivative of an integral is going to give you back that derivative. So again, the big idea is f prime of x equals d dx a to x lowercase f of t dt. They call this part 1 of the fundamental theorem of calculus. This is part 1. We are going to do part 2 today. And part 2 is all about area. So are we good with part 1? Really. So, part 2. This is actually both theorems, and I actually printed out a nice sheet of paper for you to put in your binder, so you have both theorems, one page, big, bold, easy to read. We are looking at part 2 today, which says that f is this integral, and the antiderivative of f, as long as f is continuous and closed, will give this function here from a to b of f of x dx equaling f of b minus f of a. This is what we've been talking about, essentially. It is saying, okay, this is f of b minus f of a. It is the area from one point to the area of the other. Where it's changing a little bit, or what we're doing now, is that we are going to start talking about curves that are above, curves that are below, and these antiderivatives that need the substitution method, and essentially a chain rule idea. So we're going to learn our chain rule or substitution method on Monday. We are going to finally have this rule where what happens when we have functions and functions and finding that area. In order to do that, we want to make sure that we truly understand what these graphs look like and how we're looking at their areas. So for part 2 of FTC, what you would essentially do is start by graphing your function to determine continuity. So again, a big part of the definition is that the first original function, f of x, must be continuous on the interval. If you do not have continuity, then you do not have an antiderivative. Using the methods from the previous section to find antiderivatives. So again, we're going to use what we did in 5.3. Then we're going to plug the b value into the antiderivative, subtract this value, the a value subbed in, and get a nice numerical answer. So really, definite integrals and the fundamental theorem of calculus part 2 are very, very similar. We're just going to finally have this full-blown connection between Riemann area and integration. So, what would the graph of x cubed look like from -2 to 1? Give yourself an easy sketch. If you plug in -2, -2 cubed would be if you plugged in -1 cubed would be plug in 0, plug in 1. Okay, so we have this curve. And this curve is going to have areas above and areas below. And that's kind of the big picture or the big idea. We know how to find the antiderivative. What's the antiderivative of x cubed? And our rule says, okay, this is my b, this is my a. So f of b, because this now right here, we refer to this as capital F of x. So here's your b, here's your a. So it's capital F of 1 minus capital F of 2, or in this case, 1/4 minus negative 2 to the 4th all over 4. So negative 2 to the 4th would be 16, 16 over 4. Well, we'll leave it as 16 for now because 1 minus 16 is easier, thus giving you negative 15/4. Do we logically understand that this side has way more area than this side, hence why our integral is negative? Continuous function on the interval, found our area. Okay, we have negative 3 to 1 of x to the negative 2. So again, that's kind of like 1 over x squared. So, what would your graph look like of 1 over x squared? What happens at negative 3? Okay, what happens at negative 2? What happens at negative 1? Okay, so here's my graph. What's happening to this graph as we get infinitely closer and closer to 0? Yeah, we have a what type of asymptote?
Why is it going like here? Yeah.
It still won't work because 0 is what? An asymptote either way. So whether it was to 0 or to 1, it still doesn't work because x equals 0 is a So again, it's important to understand what the graphs look like. The x-axis is our bound, but if the x value is going to this negative infinity, there is no bound to stop it. Therefore, the area would be infinite. Okay, 1 to 3 is 5 over x to the 4. Is 5 over x to the 4 a continuous function? In general, no, because 0 would be outside its domain. Are we evaluating at 0? No, therefore, is it continuous on the interval we are given? Yes. And that's what's so important, that you have continuity on the closed interval you are given. So if our interval is from 1 to 3, and we are continuous from 1 to 3, then we can integrate. So, from 1 to 3, this function would kind of look like this. Because again, we know it has that vertical asymptote at 0. So we know as we're getting closer and closer to 0, this function's continuing forever. At 1, you have 5. And at 3, you have 5 over 1. So again, we just kind of like approximated that little point. So, antiderivative of 5 over x to the 4th. If you want, you can think about it as 5x to the negative 4th. So you add 1, divide by your new exponent, and again, this represents capital F of x, this represents b, this represents a. So you have 5 Again, this is probably where it's easier to drop down your values. So you'd have 3 to the negative 3, which is like 27, but 27 times negative 3 would give you 81. It's going to remain negative. And then over here, you have minus a minus, so it becomes positive. 5
Even Horvath, please come to the office.
Wait a minute.
Even Horvath, please come to the office.
So do I call her and let her know
Let's
he's like
see.
not here? Probably. Because they'll be Scott's going to be on this video.
Hi, Steve. Hey, Steve, get that.
All right. Any questions on that so far? Next one. Go ahead and try it on your own. So find the area of that parabola from 0 to 1. I really think we should do this. Find the area under the curve for the parabola y equals x squared. Why do you not have notes?
Yeah, I left them in my binder.
You want to? Isn't there another empty? There might be a blank one in the bin.
We can do it this whole
I
time.
always.
I could do it in my
He's
notebook.
been
yeah,
reading
Jake
his
said it.
notebook before, kid. I usually always make. Is there an extra one over there? No. Hold on.
They got paid.
Nico's giving you a hard time, but Nico has his and she's not great. Here you go. You're welcome. Yeah, where were you?
Man, that was weird.
Remember the first time we saw that word parabola? We always called it parabola.
Parabolas are good.
There's a lot of kids that do that.
Wait, what's the
A hyperbola, like this scalar symbol, like that little
Oh, the
diamond
diamond
thing.
thing. Oh.
No,
It's like a storm diamond.
Yeah, it was.
I don't think I heard that before.
No, and the guy was a history teacher, and he's like, "What is this?" And I was like, "I've never heard of hyperbola." He's like, "Wait, isn't it like you think?" I was like, "That's."
I thought it was like
It's like the reverse.
It's like the you
thing.
thing.
I always just describe it as like the little scalar symbols, because that's really like what you would see, like kind of after you grab
Would you
it.
have to make
ever
like
used?
Would you have to make like?
In the scalar symbols.
Yeah, like
I don't know.
Would you have to make like? Would you have to make like a rectangle around it and then make like parabolas inside like? So weird.
Yeah, kinda.
Okay. Cut it out with.
It's gonna have like a lot of fractional like looks to it.
How are we supposed to do that to the problem?
We never get to it. Like it's
No,
part
they
of
all look
it's part of the algebra
It
too.
was
The
also
straight
Trinity.
curriculum.
Wait,
We just never get to
The
it.
Trinity logo first.
It's part of CHS.
It is.
Oh yeah,
So we
and
have-
I won't be going to teach it.
Wait, hyperbolas?
Huh? It's on CHS.
You know what I mean? It doesn't teach us hyperbolas.
Why would you ever say that?
I should call it.
Alrighty, let's
It's
check
all
this
right.
one. So I kind of, because it was in green, I like made it brighter for you.
I love the white. Look at the white text or the white and black. Like no, I don't know that. It's like one of those oversaturated.
You don't have to worry about that stuff. Okay.
Yeah, seriously, Sam.
Well,
-1.
so the reason, can you tell me why I wrote it for this one and not the other one?
Just find the area.
Yeah. So I wanted to like hint or get at, did anybody put it, but then it was already up there. So yes, the reason I have units squared is because the directions on this were different from the directions on the previous one. The directions here said find the area. Area has units. Integration does not.
We're given an x function like x cubed, like x cubed. Would it ask us to find the volume then?
No.
Is it like the significant piece of that? Yes.
We're going to do volume after this. Okay, find the area under the curve of y equals cosine x from 0 to pi halves. So again, it's very, very helpful to know, okay, where does the cosine function start? Where would the cosine function end? So the cosine of 0 is going to be
1.
Cosine of pi halves is
0.
So this function is all positive, it's all above. So again, when we're talking about area, the area is all above. So antiderivative, or rewriting this as an integral, would look like cosine x dx. The antiderivative of cosine is, evaluate sine at pi halves and 0 now. So sine of pi halves is, sine of 0 is, so the area under that curve is, and remember, we have units. I like the next one.
Yeah. I love the next one.
Oh,
Really good.
Right.
Okay.
I don't think how many papers are left on here? Hold on. We already did that. No. We already did that. Already did that. Alright, so it's just this one right here you need. Yeah, this is a good one though. Just give space, write it at the bottom, and write it off to a side. Find the area, and that's why it's in quotes, of the region between the curve y equals 4 minus x squared from 0 to 3 with the x-axis as a bound. So just start with sketching this. At x equals 0, what's the height?
4.
At x equals 2, what's your height?
0.
At x equals 3, what's your height? What happens to this curve that makes area difficult? Yeah, it goes below the x-axis, right? So when you're asked to find area of an integral, and the integral goes above and below, you have to split your derivative into parts where the 0 occurs. So what we have to do is we have to take 0 to 3 of 4 minus, this is where it gets trickier, the 4 minus x squared, and we have to split it so that it's 0 to 2 of 4 minus x squared. Now, would you be adding this area below? No. If you want the total area, what do I need to do? I need to get this graph reflected above. So how do you get something to reflect?
You just do it and change the sign.
Yeah, I would just change the sign, right? I need the inverse. I need it to make it negative. So if I subtract the negative area away, it would become positive. So what we have to do is when we have negative net areas, we have to subtract them away to turn them into positive areas. So you have to split your antiderivative at those zeros to essentially bring it back to the top. So antiderivative of 4 is 4x. Antiderivative of negative x squared is negative x cubed all over 3. And now we have to split our evaluation from 2 to 0 minus the evaluation of that same function, 4x minus x cubed over 3, from 3 to 2. So plug in your top. 4 times 2 is 8. 8, or 2 cubed is 8. So you get negative 8/3. Plugging in 0, what am I going to get? Zeros, right? Here's where you have to be really careful. That negative has to distribute to everything in the f of b minus f of a on the other part. So it is important to put parentheses here. Now plug in your top. So 4 times 3 is 12. 3 cubed is 27. 27 divided by 3 is 9. But remember, it's f of b minus f of a, so you have another negative in there that distributes to two values. So you get 8 minus 8/3. So what's your signs is the essential idea of this. So clean it up a little bit. 12 minus 9 becomes 3. Okay, so you get 8 minus 8/3 minus 3, because I'm going to distribute that negative. If I distribute a negative to a negative, what would happen? So then these just stay. Or if you wanted to, you could say, okay, this becomes positive, so this is negative, this is positive. But then when you distribute your negative again, it's like, okay, that becomes positive, that becomes negative. Combine like terms. So 8 plus 8 is 16. 16 take away 3 is 13. Negative 8 gives you negative 16/3. So 13 minus 16/3 means I need a, yep, so multiply by 3 on top and bottom. So 13 times 3, 39 minus 16. What did this ask me for?
Area. So is it, so it's the 0 to 2, and then adding the 2 to 3. So the 2, like, is it like kind of like the absolute value of the area?
It would be the absolute value of the integral. So area is like the absolute value of integration. Just to like say it kind of like more correct. So essentially what we did was we subtracted a negative area. If you found the integral from 2 to 3 alone, without this negative right here, this value would have been negative. So if you think about that fact right there, you kind of ignored this negative sign, and you did 3 minus 8. Can't you see right away that's negative 5? Negative 5 plus 8/3 is going to give you a negative number. So this would have been negative. However, by subtracting that negative, we essentially made it positive by reflecting our graph upward to give us the actual area. this value right here is not equal to the integral value. Is that what you're going to ask?
I was going to ask, like, when do you actually, like, subtract it normally? Just in the integral value?
Right, so if we found the integral of this curve from 0 to 3 of 4 minus x squared
Would be a
dx.
positive area minus that area below the line.
What do you
Well,
just plug in 3 at the
basically.
top?
Yeah,
and then
that's what I was
subtract
saying.
the
It would
other.
actually be 4x minus 1/3 x cubed evaluated from 3 to 0. So it would be 12 minus 9, right? 27 divided by 3. So the integral value is 3. The area under the curve is 23/3.
Area is
So for the area, we basically flip it up, right?
Correct. You have to make everything above the x-axis. So that's like kind of the point of that is if it asks you for area, you need to make it above the curve. All right. I'm debating if I want to be in the book or on a handout. Actually, no, I'm going to do something.